Hey kiddios, okay, so this video is going to be over section 4.4, okay, and this deals with oxidation and reduction reactions. Now, I don't want you to be intimidated by this because once you get the hang of it, it becomes easier and easier as you do the practice problems, okay. One big thing that's going to help you tremendously when it comes to this chapter or this section is oil rig, okay, and what it represents is oxidation is lost, and we'll talk about what it's losing here in a second, and reduction is gained, okay? So oxidation is going to be when we lose electrons, so electrons get lost and electrons get gained, okay? And whenever one electron gets lost, an electron has to be gained, okay? So our definitions for this chapter or this section are going to be oxidation and reduction. Oxidation is when electrons are lost and things become positively charged or become less charged than they were, I guess is what I should say. Where if I have reduction, that means I gain electrons or become negatively charged or become more charged. Okay. So example here, when sodium Na goes to sodium ion Na+, that means it's being oxidized, meaning it's losing an electron. Where fluorine, when it becomes F1-, that means it's becoming reduced because it's gaining an electron. Okay. Now there's some oxidation rules that you need to know in order to count these oxidation numbers for these things, okay? And those are as follows. If something is in its elemental form, it's going to be a neutral charge of 0, okay? So it's not going to have a charge. So for example, neon is in its natural state, so it's going to have a charge of 0. Nitrogen is a diatomic molecule, so it's going to be 0 as well because there's 2 nitrogens attached to it, and that's its natural state. Iron, a metal, is going to be a 0 charge in its natural state. And then oxygen is the same thing. It's a diatomic, so it'll be 0 because it's in its natural state, or it's in its elemental form. Okay. Monatomic ions, meaning one ion that's present, is going to have the charge that that ion carries. So for example, calcium +2 is going to have a +2 charge. Okay. Nonmetals are going to have negative oxidation numbers. Okay, so that means most of the time they're going to be reduced. Oxygen's usually going to be a -2, except when it's a peroxide. So if you ever see something like H2O2, K2O2, Na2O2, okay, that means that the oxygen is going to be a -1 charge, okay, because the hydrogen is always going to have a +1 charge, and you need things to cancel, okay. So for example here, in this example, we know or we remember that the charges get uncrisscrossed. So here, hydrogen's oxidation number is +1 and oxygen is going to be -2. Okay, now in this case down here, hydrogen cannot have a +2 charge, which means that if I have 2 hydrogens with a +1 charge and I add that to my 2 oxygens and try to figure out its charge, okay, if I solve for x, x is going to equal -1. So both of the oxygens in this compound will have a -1 charge. Okay, and we'll look more at that here in a second. Hydrogen is usually a +1 when it's bonded to nonmetals. So here was our example there. Hydrogen is being +1, and it's going to be -1 when it's bonded to metals. Okay. So it acts like a metal when it's bonded to a nonmetal, and it acts like a nonmetal when it's bonded to a metal. Fluorine's always going to be -1, and halogens, our group 17, is always going to be -1, except when an oxyanion, they are going to be positive. Okay, we don't see these very often. However, you should at least know that. You probably won't be tested on it, but just keep that in mind. Okay, and then the sum of the oxidation numbers of a neutral compound is going to be 0, and the sum of an oxidation number of an ion is going to equal the charge of that ion. So for example, H2O, since there's no charge on the overall compound, its overall compound is a 0 charge. Where the nitrate ion, which is NO3-1, this overall ion is going to have a charge of -1. Okay? And we'll look at examples, so this will be very clear when we do those. So number 3 thing is oxidation of metals by acids and salts. These are just basically single replacement reactions. Okay? A goes in, kicks B out, and then B is now by itself. Okay? And with that being said, if we're having a single replacement reaction, we need to think about an activity series. Okay? And an activity series are just the metals listed in order of decreasing ease of oxidation. Okay? So oxidation is going to be losing or gaining electrons. Okay, so the easier it is, decreasing. The easier it is to remove the lower it is on the scale. I'm sorry. Okay, so let's look at some practice problems. You're going to have to do these, or at least try these problems for homework. But let's go ahead and look at some practice problems on page 138. Okay, 138, sample problem 4.8. It wants us to determine the charge of sulfur in each of the compounds listed. Okay, so the first one says it's H2S. Okay, so we are tasked to find the charge of sulfur. Okay, now hydrogen is attached to a nonmetal, therefore its charge is going to be +1. Okay, and if I uncross, that turns out to be true. So sulfur's charge in this case is -2, and hydrogen is +1. Another way that you can think about this is you can say, well, I have 2 hydrogens at a +1 charge plus 1 sulfur with an X charge, and since there's no charge on it, it's going to be equal to 0. So it's going to be 2 plus X is equal to 0. Subtract 2 from both sides. So X is going to be equal to -2, so sulfur's charge is -2. Okay? The next one is S8. Okay? This is sulfur in its natural state. So therefore, that means that sulfur's charge is going to be 0. Okay? No charge. The next one is SCl2. Okay? Chlorine's a halogen, so it's going to have a -1 charge. There's no overall charge, so I'm going to say I have 2 chlorines at a -1 charge plus X is equal to 0. So this is going to be -2 plus X is equal to 0. Add 2 to both sides. So X will be equal to +2, which means in this case, sulfur is a +2 charge where chlorine is a -1. Okay, let's do one more. Okay, so this is going to be sodium sulfate, or sulfite, I'm sorry. So sodium sulfite, what's the charge of, of sulfur in here? Okay, now there's 2 ways that you can do this, okay? I like to get rid of the sodium and then deal with the polyatomic ion, okay? So I know sodium's charge is +1 because it's an alkali metal and it's in group 1. Okay? So I know that I'm dealing with sulfite, which is SO3 -2. Okay? And it's a lot easier for me to figure out sulfur here because now I just have to deal with oxygen. Okay? So I'm going to say I have 3 oxygens at a -2 charge plus my 1 sulfur. And since I have an overall charge here, it's no longer equal to 0. It's going to be equal to -2. Okay? So 3 times -2 is -6, plus X is equal to -2. If I add 6 to both sides, X is going to be equal to +4. So in this case, sulfur is a +4 charge, oxygen is a -2, and then sodium is my +1. Okay, so that's how you do those types of problems. Let's look at another sample problem on page 4.9. Okay, so 4.9, it's asking us to write a net ionic equation for a compound and then to find out who's being oxidized and who's being reduced throughout the chemical reaction. Okay, so let's see here. Okay, so the question states, if I have magnesium and cobalt 2 sulfate, okay? So what that means is I have magnesium solid plus cobalt 2 sulfate. So cobalt, it's telling me it's a +2 charge, sorry. Sulfate is a -2 charge. Okay, so the charges are going to cancel. So cobalt 2 sulfate will be cobalt sulfate. Okay, and this is going to be an aqueous solution. Okay, so what's going to happen here is if I look at the activity series, will magnesium kick cobalt out? Magnesium has to be higher than cobalt. Okay, so here's magnesium here. That's magnesium here. Cobalt is here. So yes, magnesium will come in. It will kick cobalt out. So then I will have cobalt solid here, and then magnesium sulfate on the other side here. Okay. So with that being said, I'm going to have the only thing that's going to cancel is that I have these sulfates that are in aqueous form. Okay, so I need to take a step back and say, well, I have magnesium solid plus cobalt +2 aqueous plus sulfate aqueous going to cobalt solid plus magnesium aqueous plus sulfate aqueous. Okay, so since the magnesium is solid over here and an ion over here, it cannot cancel. So the only thing that's canceling is sulfate because it's on both sides. So the net ionic equation is going to be magnesium solid plus cobalt aqueous, and I am making cobalt solid and magnesium ion. Okay, now this one's pretty easy to identify who's being oxidized and who's being reduced. So we're going to look on either side of the chemical reaction. So in this case, magnesium is in its elemental state, therefore it'll have no charge, where over here it's +2. When I go from having no charge to a +2 charge, that means that I am losing my electrons. So I'm losing electrons, and oxidation is lost oil, so that means that magnesium is being oxidized. And then when I go from cobalt +2 to cobalt, that means I'm going from having fewer electrons to a neutral charge, so I'm going from +2 to neutral, which means I'm gaining electrons. Reduction is gaining. So it's gaining electrons. Therefore, cobalt is the species being reduced. Okay, so that's pretty much it for section 4.4. We'll do tons of practice with this, so make sure you write down any questions you may have. Thanks.